Hello guys, today we continue to discuss inductance, and we will start with the deriving equation for the energy of magnetic field, like specific energy of magnetic field per unit volume. Proceed with mutual induction phenomena. And we'll spend the rest of the time describing and analyzing LC circuits, means circuits based on inductor and capacitor, and also RLC, resistor, inductor, capacitor, electric circuits. So we have quite a lot of material for today. That's why let's go into it. Let's change the camera. So, as I mentioned, we start from energy in magnetic field. The electric circuit with an inductor and like battery needs in electric circuit with an inductor, electric battery, which provides energy to the system, needs to provide some extra energy besides Joule length heat, which is dissipated on resistor, and that is some additional energy which is accumulated in form of magnetic field in the inductor. So in general, we can write that total energy provided by battery, which is the product of electric current and electromotive force of the battery, will be equal to I squared times R plus, and here we have L times I di over dt. So it's actually the product of induced electromotive force at the inductor due to the change of electric current over time times electric current. So we can distinguish between two components. So first one is dissipation on resistor R, and second is actually accumulation of energy in the form of magnetic field. Okay, then the change of energy over time, which is accumulated in the inductor, obviously can be represented by this term. So we can write du over dt is equal to L times I times di over dt. So from here, differential of energy will be L times I times di. So with this equation, we can integrate it and get, so in order to get the full energy accumulated in the form of magnetic field in the inductor, we need to integrate this equation from 0 to I, to actually that current which is flowing through the circuit. So it will be U is equal to integral from 0 to I times L times I di. So L inductance is a constant parameter. So we can factor it out from this integral sign. And here is I times di. So eventually we get 1/2 times L times I squared. So this is the expression of the energy of magnetic field concentrated, stored in inductor when this current I is flowing through the electric circuit and inductor itself also. So this is this equation is quite similar to the equation for the electric energy accumulated in a capacitor. If you remember, we derived that previously. That was 1/2 C times delta V squared. And now, assuming that we have some our inductor in the form of a solenoid, we know that inductance of a solenoid is equal to mu naught n squared times V. And magnetic field created by solenoid. Also for both cases, we assume solenoid which interior volume is filled by air or just empty vacuum. There is no any magnetic magnetic material in there. So magnetic field vector, like absolute value of magnetic field vector will be mu naught times n times I. So with these two equations, we can proceed further in order to calculate the density of specific energy of magnetic field per unit volume. So from the last equation, we can express electric current in terms of magnetic field. So it will be B divided by mu naught times N. So where N is number of turns in this solenoid per unit length, as you remember. And now we can substitute this equation and this equation instead of L and I. So what do we get? So energy of this magnetic field accumulated in this solenoid will be 1/2 times Li squared. This is equal to 1/2 mu naught n squared times V, which is the volume of the solenoid. And then we have this electric current I. So instead of electric current, we have B over mu naught times N squared. And when we open this parenthesis, we get the final expression, which will be B squared divided by 2 times mu naught times V. So this is total energy, and we want to get specific energy per unit volume. So it will be U divided by V, by volume. And in this case, we just cancel this volume in the numerator. So we will get B squared divided by 2 mu naught. So this is very important equation because it gives us a specific energy of magnetic field per unit volume. So let's proceed further, and we can consider now one example. Some electric circuit where electromotive force, like the battery, is eliminated from the circuit, and we have the case when from maximum current starts to attenuate and decreases over time. So we considered this case during previous lecture. So we derived such equation for the time dependence of electric current, which is initial electric current times exponent minus R times T divided by L. So we want to see where this what will be the energy dissipated at the resistor connected in series to inductor in this electric circuit, and compare it to the energy of magnetic field. So the goal is to show that the total energy dissipated at the resistor will be equal to the energy accumulated initially in the form of magnetic field in the inductor. So let us do this. So the rate at which energy will be dissipated at the resistor is electric current as a function of time square times resistance. So we know the expression for this electric current, and that's why we can write that I initial times exponent minus R times T over L in the second power times R. So this gives us I initial times R exponent minus 2 times R over L times T. Okay, so now in order to get the total energy dissipated, we need to integrate it over time, and like from zero initial point when we start, when we eliminated electromotive force of the battery, and let this established saturated current, initial current, to decrease over time while running through the circuit of resistor and inductor connected in series, and from 0 to infinity. So now will be electric current initial square. Oops, sorry, here I forgot square. Square times R times exponent minus 2R over L times T dt. So initial electric current and resistance, these are constant parameters. So we will integrate only exponent function. Exponent minus 2r over L C dt. In order to integrate this, we need to get the same argument in the differential. So in the differential, we should have the same expression as the argument of the exponent function. In order to do that, we need to multiply this everything with minus L over 2r. Here, then we have integral 0 from 0 to infinity, exponent minus 2r over L times t, d minus 2r over L times t. Okay, now we can easily integrate this. Let's go to another slide. And this will be minus I initial square times R times L over 2R. And here is our exponent function minus 2R over L times T from 0 to infinity. So here, if we consider infinity for time t, this exponent will give us 0, because here we have minus in the argument of exponent, and at time equals 0, that will be exponent with the argument 0, which gives us unity. So it will be minus 1. This minus 1 and this minus, which we have in front of this expression, will cancel out, and we will eventually get I initial square times R times L divided by 2R. So R we cancel out, and we get the final expression I squared times L divided by 2. So this is the expression for the energy accumulated in the energy of magnetic field accumulated in the inductor, which we derived just a few minutes earlier. So we have shown that all energy, assuming that connecting wires don't possess any resistance, all energy accumulated in the inductor is transformed in Joule length heat dissipated at the resistor. Now we proceed further with mutual inductance, and it's necessary to mention that very often the magnetic flux through the area enclosed by a circuit varies with time, and as a result also induced electromotive force and current in this circuit varies, is generated. So because of time varying current in nearby electric circuit. So from this figure, you can clearly see what is going on. So 1 second, I will share my screen. So here we have coil 1 with N1 turns of the wire, and some current I1 is flowing through it, which is, let's say, time dependent. Then there is certain flux of magnetic field through the nearby located coil 2, with respectively N2 turns and some current flowing through it, I2. So definitely if we change current I1, the magnetic field flux through the coil 2 will change, and that will result in certain induced current, electromotive force, and current in coil 2. So in order to describe this phenomena, which is called mutual inductance, it's necessary to deal with such a parameter as mutual induction, which depends on the geometry of these coils and their location with respect of each other. So let us come back to the slides. And we can denote, let's say, magnetic field flux F1 through the coil 1 because of current I1 flowing through this coil. So let us show here schematically, just from the side, these two coils. We have coil 1, coil 2, with N1 and N2 turns each, and there is some current I1 and current I2 flowing through these coils. So there is some magnetic field flux through coil 1 because of current I1 flowing through it. So this is quite obvious. However, there is also some magnetic field flux through coil 2, which is F12, caused by the current I1 in the coil 1. So this is what we explained previously, and there is certain parameter like mutual inductance M12 of coil 2 with respect to coil 1. So as I said, this parameter depends on the geometry of the coils and their alignment with respect to each other. So M12 could be given in terms of N2 times F12 divided by I1. So like magnetic field flux through the coil 2 because of electric current flowing in coil 1, and these coils are located close to each other. So then if I1 is time dependent, then according to Faraday's law, there will be some electromotive force induced in coil 2 because of changing current in coil 1. So it will be epsilon 2 equal to minus N2 times dF12 over dt. And if we substitute now expression for this magnetic field flux through coil 2 because of current in coil 1 will be N2 times d over dt, and here is M M12 times I1 over N2. So this will be equal to minus M12 times dI1 over dt. So we see that the induced electromotive force in the coil 2 will be proportional to the rate of changing electric current in coil 1, and also proportional to this coefficient which defines the mutual inductance of these coils, M12 of coil 2 with respect to coil 1. So let us go further. We actually can write the similar, the same equivalent equation for induced electromotive force in coil 1 because of changing current in coil 2. That would be minus M21 mutual inductance of coil 2 with respect to coil 1 with respect to coil 2 in this case. And here is the rate of changing current in the coil 2. So it's actually possible to show that mutual inductance of coil 2 with respect to coil 1 is equal to mutual inductance of coil 1 with respect to coil 2. And that is just some parameter which is called mutual inductance of these two coils connected, located close to each other. And of course, also will depend on their geometry. So that's why, in general, it's possible to write for epsilon 1 will be for electromotive force induced in coil 1 as minus m times di 2 over dt, and epsilon 2 equals to minus m di 1 over dt. So this is pretty much everything about mutual inductance, and should also mention that units for measuring mutual inductance is the same as units for measuring inductance, and that is Henry. Okay, so now we proceed further and consider oscillations in LC circuits. So LC circuits, it's a circuit obviously which consists of capacitor and inductor. So let us consider such electric circuit. With a switch S, capacitor C, inductor L. Capacitor initially is charged, plus minus. And let us think what will happen when we turn on this switch S. So since this capacitor is charged, it accumulates certain energy, so it has some electric charge Q maximum. It's maximum charge which is accumulated at this capacitor, this given example. So there will be some energy accumulated in this capacitor, which is equal to Q maximum squared divided by 2C. And at T equals 0, electric current is equal 0. So we just turn on the switch, and there will be some electric current flowing through the system, this electric circuit. And initially, since electric current was equal to 0, there was no energy accumulated in the inductor in the form of magnetic field. But once this current starts to flow through the circuit, then we kind of transfer energy accumulated in capacitor in the form of electric field. We transfer it to energy accumulated in the inductor in the form of magnetic field. So that will happen until electric current doesn't reach its maximum value. Then capacitor will be fully discharged, and all energy will be in this electric circuit accumulated now in the inductor in the form of magnetic field, and that will be L times I maximum square divided by 2. So once we reach this moment when current is maximum, it will continue to flow through the circuit in the same direction, but it will start to decrease. And while this will happen, our capacitor will start to charge. So it was discharging always up to current reached its maximum value. And at some point, when this maximum current has been reached, after that, current will continue to flow, it will decrease, and capacitor will start to charge, but will charge with a different polarity. So that will happen until all energy accumulated in the inductor in the form of magnetic field will not transfer back to the capacitor, which will be fully charged with the charge Q maximum. What is also important to mention that in this circuit we have only capacitor and inductor, means there is no electrical resistance, and that's why we don't have any energy dissipation. So this is quite similar to what we considered in the mechanical oscillations of the system block spring. So let us share again the screen to show you. Okay, we share the screen, and here we have this comparison. As we considered initially, we have fully charged capacitor. All energy is accumulated in the capacitor, and this is equivalent to stretched string. It gains some potential energy and zero velocity. So then we discharge this capacitor, reach maximum current, which corresponds to maximum velocity of this block, and minimum potential energy, which is zero at equilibrium position. And in this case, energy is totally accumulated in the inductor. However, total energy of the system always remains constant, doesn't matter where it goes. So again, after fully discharging the capacitor, the current continues to flow, and this capacitor is charged again back to maximum charge, but with different polarity. So that also results in accumulation of energy in the capacitor, which is equal to total energy, and there will be zero current, so zero energy is accumulated in the inductor. It will be again like another extreme position when maximum potential energy, but velocity of the block is equal to 0. So this is the way how we can find the analogy with these two different types of electromagnetic and mechanical oscillations. Also, what is important that if we have some intermediate case when a capacitor is still not fully discharged and electric current hasn't reached its maximum value, we have some energy accumulated in the inductor in the form of magnetic field, some energy in the capacitor. So in analogy to the mechanical system, we have certain potential energy still remaining and also some velocity already not equal to 0. However, the sum of these two energies will again give us this constant total energy in the system. So now, taking this into account, that total energy in the system in any time, any arbitrary moment of time is constant, we will proceed further in order to develop quantitative model which describes this type of electromagnetic oscillations in the LC circuit. So let us stop sharing the screen. And let us consider some arbitrary time t when Q is smaller than Q maximum and current is smaller than I maximum. So then we deal with some intermediate values for accumulated electric charge and current flowing through the circuit. So total energy of the system is energy accumulated in the capacitor plus energy accumulated in the inductor, and that is equal to Q squared over 2C plus 1 second times Li squared. So this at any moment of time is constant, right? Constant. So how do we define this? That certain function is constant. We define this with a derivative over, so constant in time, du over dt is equal to 0. So that is the condition that there is no change of this function over time. So let us do this. We can write that this will be equal to d over dt q squared over 2 times c plus 1 over 2 Li squared. And this will be equal to qc over c times dq over dt. So how we get here, we take derivative of this term and consider that q is a function of time, so we need to multiply by derivative of this term by derivative of q over time. And the same we do for the second term, which will be L times I times di over dt. So this is equal to 0. Assuming that electric current is the rate of changing of electric charge, so which is dq over dt, we can substitute expression for I and also expression for the derivative of di over dt as d squared q over dt squared. So once we substitute I and di over dt with these expressions, we will have now only one variable, which is electric charge, and we'll get final differential equation, which will describe time dependence of electric charge accumulated in the capacitor. So let us get this differential equation so we can get eventually Q over C plus L times d squared Q over dt squared, and this will be equal to 0. So what we did, we divided the previous equation by electric current I. So maybe let us do this step by step so it will be more clear. So on the previous slide we had, let's take a look again. Okay, this is what we need. du over dt is equal to q over c dq over dt plus L times I di over dt. So this is equals to 0. So we know that this derivative is equal to I. So we have actually I in the first term and I in the second term. So what we can do, we can just divide this by I and then substitute this derivative di over dt with the second derivative of electric charge over time. And now we get this equation, Q divided by C plus L times d squared Q over dt squared. This is equal to 0. So after rearranging, we will get d squared Q over dt squared is equal to minus 1 over LC Q. Okay, yes. So this is similar, this differential equation which we got here is similar to the differential equation for mechanical oscillation of this block spring system, where we had d square x over dt square equal to minus k over mx. So we already solved this equation in our Physics 1 course in detail, so we will not repeat that. We just know that the solution of this equation comes in the form of some amplitude value times cosinus omega t plus phi. Who is interested, you can check our recorded video lectures from the first semester, we will use similar, like the same form of solution for our differential equation, which describes electromagnetic oscillations. So, and that's why we will get Q equal to Q maximum times cosinus omega t plus p. So omega is angular frequency, and phi is some initial phase of this oscillation. So let us keep this in mind and go further. In our case now, omega, this angular frequency, will be equal to 1 over square root of L times C. So this is a so-called natural frequency of oscillations of the LC circuit. So electric current which is flowing in this circuit, we know that it's derivative of charge over time, and that will be minus omega times Q maximum times sinus omega t plus p. So now we need some boundary conditions in order to figure out what is this in our particular case. What will be the initial phase phi? So we know that at t equals 0, electric current is equal to 0, and electric charge is equal to Q maximum. Setting I equals 0 and at t equals 0, we get the following. So in this equation, I mean, setting this condition. So 0 is equal to minus omega Q maximum sinus phi. And from here, we obviously see that phi is equal to 0. So this condition also satisfies equation for the charge, because we have Q is equal to Q maximum times cosinus omega t plus phi. So we know that at t equals to 0, Q is equal to Q maximum, means that phi should be, so here we get 0 because t is equal to 0, and here should be also 0 in order to get cosinus phi equals to unity. Then the charge will be equal to Q maximum. So this condition satisfies both equations, and final expressions for time dependence of electric charge accumulated in the capacitor will be Q maximum times cosinus omega t, and electric current as a function of time will be minus omega Q maximum sinus omega t, or it could be minus I maximum sinus omega t. So now let us consider the final part of our today's lecture, how energy can be described in terms of these derived equations for electric charge and electric current. So we know that total energy accumulated in the system is energy accumulated in the capacitor and inductor. So we can write that Q maximum square divided by 2C cosinus square omega t plus 1/2 L I maximum square times sinus square omega t. We know that these amplitude values, they are equal to each other because we can fully transform energy accumulated in the capacitor into energy accumulated in the inductor. That's why we can write that they are equal. And that means that we can just factor out, for instance, Q maximum square divided by C. And in the parentheses will be cosinus square omega t plus sinus square omega t. So let us do this. So U is equal to Q maximum square divided by 2 times C. Here we have parentheses, cosinus square omega t plus sinus square omega t. So this is equal to unity. And that's why total energy is Q maximum square divided by 2 times C. So this is correct from our previous discussion that the sum of energy at any given time is a constant parameter defined initially by the level of charging of electric capacitor in the circuit. So this is constant. So at this point, we will finish our lecture and continue on Monday with resistor, inductor, capacitor circuits. When we have some resistor where energy can dissipate, and that should be taken into account in order to quantify, like, Derived equation, which describe so-called damped oscillations, electromagnetic oscillations, when the amplitude of electromagnetic oscillation and amount of energy accumulated in the system will decrease over time. So that we will do on Monday, and that will be the last step prior our new topic, which will be focused on alternating current circuits. So we discussed previously DC current, and now there will be another big topic and very important, alternating current circuits. So we will have quite a lot of material for the next week. Thank you very much for attention, and have a good evening. Bye.